So in this final example, I'm going to do something somewhat different. I'm going to apply Gauss's law to a gravitational field rather than an electric field. And that might sound odd, given that this course is about electricity and magnetism. But really, this course is about understanding the relationships between laws, understanding the relationships between mathematics and physics, understanding scientific reasoning, and so on and so forth. So this topic is totally on point. So there is a Gauss's law for electrostatics, and we kind of derived that using our understanding of the electric field and electric field lines and so on. Go back to part 1 if you need to review that. So you can do exactly the same thing to the gravitational field. In the gravitational field, we're going to write a little g, right? A little g here, and by g I don't mean 9.8. That's just the value of the gravitational field at the surface of the Earth, with the direction being towards the center of the Earth, right? But it's just the value in the particular spot where we're at. In general, it's given by this. And you remember, maybe you haven't seen this exact form, but you've probably seen, or you hopefully have seen, is Newton's law of gravity, where the gravitational force is g(m)m/r². The same way, the electrostatic force between two charges is k, 1/4πε0, times first charge, second charge over r². And we define the electric field then as the force per coulomb of charge. So what's the force? What would be the force if you placed 1 coulomb of charge in a particular spot? That's what the electric field at that point, right? That's kind of what we mean. Same thing here, right? If this is the law, then I can say, well, what's the force on 1 kilogram? If you plug in 1 kilogram here, at a particular point, if that 1 kilogram was put there, well, that is the gravitational field, right? And if you're on the surface of the Earth, plug in the mass of the Earth, you plug in the radius of the Earth, you multiply by this constant, the gravitational constant, and you get 9.8. So there's this exact analogy. It's just you probably met this in 161 or a similar course, not necessarily thinking about it in this field way, but everything we've done with the electric field you can do with the gravitational field. So this analogy, right, comes from the fact that both laws are essentially 1/r² laws. There's a constant. In one case we call it k, or 1/4πε0, but that's just rewriting the constant. In the other case we call it g. Then you multiply the two charges. Here you've got masses, right? Gravity acts between masses. Electrostatics acts between charges. But these are just, the physical properties of some object. How heavy is it? How much mass does it have? How much charge does it have? Mathematically, it's exactly the same. And so we come to this, this sort of translation from charges to masses from 1/4πε0 to g. Right? Those are the 1/4πε0 takes the role of g. So you can do the derivation we did in part 1, talking about gravitational flux and so on. You can do all that, but we're not going to. I'm just going to put down this sort of translation and then write down Gauss's law of gravity. So Gauss's law for electrostatics was E dot dA over some closed surface is Q inside over epsilon naught. And now I'm going to translate with some closed surface. And I don't have an electric field, I've got a gravitational field, but I'm still integrating over the little chunks of area making up that whole sphere. And now it's not a charge inside, it's the mass inside, divided by, well, it was epsilon naught here, but 1/epsilon naught is 4 pi g. So actually, I'm just going to multiply by 4 pi g, right? So it doesn't quite fit. Mass inside times 4 pi g. That's Gauss's law for gravity. It's almost like I've just changed the letters I use. right? That's it. Same thing. So we're now going to do an example that's a bit more complicated than what we had before. And we're going to do it with gravity. But there's an analogous example in electrostatics. So we talk about a gravitational field inside the Earth, and the Earth, we're going to treat it like it's a solid sort of sphere of constant mass density. So, you know, any cubic meter of Earth you dig up has the same amount of, has the same mass. That's not quite true, right? For example, the Earth's core is a lot denser than, say, a cubic meter of ocean water. That's also part of the Earth. Or a cubic meter of rock even, right? So it's not true, it's not exact, but we're going to go with it. And analogously, you could think of a ball of charge where it's not just on the surface, but the charge is sort of spread out over the whole volume of the ball. Right? You can do that example in just the same way we're going to do the gravitational field inside the Earth. So we have Gauss's law for gravity set up. Right? It has this 4 pi because, like, it's sort of a trade-off, right? Here there's no 4 pi in the law here, but there's a 4 pi here. But then there's the 4 pi goes away in Gauss's law, well, but instead we have it here. But it's just a numerical factor that's easy to deal with, right? That just makes it look a bit different. Okay, so here's the Earth. I'm not going to attempt to draw the Earth on it. Just going to make it messy, like the surface of the Earth. So here's the center of the Earth. The Earth has a radius r. And I want to figure out, right, the gravitational field inside the Earth. So imagine you dig a hole to some depth, say here, half the way down, something like that. What's the gravitational field here? Now, normally if we dig down like a tiny bit, it's still 9.8. It's so close to the surface. But if we dig deep down, what is it there? What is it? A radius r away, little r. Now, if we were outside, you know what it would be. It would be, you know, G, big G times the total mass over 4 pi. Sorry, big G times m over r squared, right? So the gravitational field here, it's always attractive, would be G, mass of the Earth, divided by distance squared. You know, remember, right? Distance squared. Distance to the center squared. Right? And that is just applying Gauss's law in the same way we applied in example 1 with the spherical shell. If this were a spherical shell with the mass all in the shell and hollow in the middle, we'd know the gravitational field here would be 0. Just by the same logic that we applied to the inside of the hollow charged sphere, right? It's exactly analogous. But now, the mass of the Earth isn't all in a shell near the surface, it's evenly spread out across the whole Earth, at least in our example. Let's apply Gauss's law, just the same way we did with electrostatics. Well, we want the gravitational field here. By the symmetry of the setup, G is gonna point down like this. I mean, I guess it could point outwards, but it has to be radial. I'm going to pick my surface to match the symmetry. My Gaussian surface S is a sphere of radius. Oh. We're going to assume r is smaller than the radius of the Earth. Right? Okay, so let's apply Gauss's law of gravity. The logic for the left-hand side of Gauss's law is exactly the same as it was in example 1 with the spherical symmetry, right? So spherical symmetry, so the gravitational field is going to be the same everywhere here, except it's always radial, right? It can't be at an angle because that would violate the rotational symmetry of the whole setup. what's the angle between the flag and the gravitational field? Well, the flags on my surface go like this, right? So if I figure out a little area here, then the angle is going to be 180. So the cosine of 180 is -1. The minus sign is just going to tell me that it's essentially attractive, right? As if I'd had a negative charge. So the flux, write this down. Flux through one of those tiny windows, dA, what is it? It's going to be G dot dA, which is going to be the value of G, which is constant, right? It's the same here as it is here as it here. It has to be. If G was bigger here than here, then the gravitational field would not be spherically symmetric, whereas the mass distribution is spherically symmetric. That would be essentially a violation of the symmetry. Right? The gravitational field has to match the distribution of the mass in terms of symmetries. This is the value of G times dA times, well, I guess I could put a -1 here. I guess I'm going to do it. Cos 180. So this is going to be -1, but we're just going to end up with a minus sign in the end, right? And all that's going to tell us is that Gauss's law is attractive in this case. So the total flux by flux, I now mean gravitational flux, is going to be phi g, right? Gravitational. It's going to be G dot dA, and the integral being taken over our surface S, but G is constant. There's a minus sign, minus G times the area. That is just a sphere, right? This is exactly the same we had before in example 1. This is just going to get you 4 pi r squared, the area of this green sphere. Right? The imagined Gaussian surface that is a sphere of radius little r, where little r is the distance from the center where we want to find the strength of the gravitational field. Okay, that was easy. Are we done? No. Right? The difficulty now, the reason this is an interesting problem, is because the mass is, well, is it inside or outside? Well, some of the mass is outside, some of the mass is inside. Right? So this is like solid rock, or solid magma, whatever you want it to be. Some of the mass is inside it, some of the mass is not. Right? The mass out here is outside, the mass in here is inside. So what is the mass inside it? What is the total mass inside? That's going to be next part. Start a new sheet for that. Right, M inside. So if you're assuming that the Earth has a uniform mass density, so any cubic meter, pick a little cube in here, that has the same mass as the same cube taken from here. Right? I'm assuming those are the same mass. That means that the fraction of the Earth's mass that is inside here is just a fraction of the volume that is inside here. So if half the Earth's volume is inside this sphere, then half the Earth's mass is inside the sphere. If 1/8 of the Earth's volume is inside that sphere, then 1/8 of the Earth's mass is inside that sphere. Right? So M inside is the mass of the Earth times the fraction of the volume that's inside S, the fraction volume inside S over the total volume of the Earth. Right? Hope that makes sense to you. Okay. So the mass of the Earth is what it is, something like 6 times 10 to the 24 kilograms. Exact value doesn't matter. The volume inside, well, what's the volume of the inner sphere? Well, a sphere has 4/3 pi r squared, right? That is the volume of a sphere. So the inner sphere, the Gaussian sphere, has a volume 4 pi r cubed, right? It's a volume. Whereas the Earth has a volume 4 pi r radius of the Earth cubed. I guess I could call this radius of the Earth. Now, conveniently, right, bunch of stuff here cancels out. So the mass inside is just the mass of the Earth times r cubed over big R cubed. The radius, that is the distance of our point from the center, the point where we want to find the gravitational field, that cubed over the radius of the Earth cubed. That's going to give us the mass inside. Okay, now we can plug this into Gauss's law for gravity. So we get, right, let's write it out. Just again one time. The left hand side, we've got a gravitational flux, G dot dA. That is going to be equal to 4 pi g, right? That was the equivalent of 1 over epsilon naught times the mass inside. We've worked out the left-hand side, we've worked out the right-hand side. This was the left-hand side, minus g times 4 pi r squared. So we get minus g times 4 pi r squared is equal to 4 pi g times the mass of the Earth times r cubed over r Earth squared. Okay, we can simplify that, and we find that g, right, the 4 pi is going to cancel out. A bunch of the r's are going to cancel out. This is cubed, this is square. Right, the area of our ball that figured into the flux increases as r squared, whereas the volume that determines the mass inside increases as r cubed as we keep going further out from the center. That's why we get these different dependence. But then we can simplify this, and we're going to get g, I guess the minus sign, g me. Then I'm going to get r squared cancels 2 powers here over r Earth cubed. Now that's interesting, right? This is a linear function of r. Those things are constant. The minus, okay, it's downwards. Let's do a sanity check. At this surface of the Earth, little r is equal to the Earth's radius, right? If I want to find the gravitational field at the surface of the Earth, I plug in radius of the Earth up here, and so then I'm going to get it's going to cancel one of those powers here. I get back Newton's law of gravity. Let's write this down. Sort of sanity check. At surface, r is equal to r Earth. So g is equal to minus g me, and then I get 1 over re squared, because the plugging this into here is going to cancel one of the powers. Okay, that makes sense, right? That is just Newton's law of gravity given back to us. But as long as we're inside, there is a linear dependence, right? It's not squared or cubed, it's a linear dependence. As soon as we go outside the Earth, if the distance from the center where we want to find the gravitational field is bigger than the Earth's radius, then the mass inside is just the mass of the Earth, right? It doesn't keep growing if you go out into space. The mass of the Earth, it's all going to be inside your imagined ball, imagined Gaussian surface, once the radius of your Gaussian surface is bigger than the actual radius of the Earth. So it's linear dependence inside, so the further out you go, the bigger the gravitational field. Right at the center, it's 0. Center of the Earth makes sense. The masses in all directions around you equally. So, and outside the Earth, it's 1 over r squared. So what we get, if we plot this on a graph, and I want to ignore the minus sign, obviously, that just says, look, it's attractive. As we go out, is right when we're at 0 radius, it's nothing. It keeps going up linearly until we get to the surface. And here, let me just show this to you, the slope is gme times 1 over r e cubed. gme over r e cubed. Oops, you can't see this, too far down, there you go. And then, once we hit the surface, if we keep going further away, well, now the mass inside the Gaussian sphere is constant. So now we just get the normal 1 over r squared fall off. Right, this is just Newton's law of gravity. Gme over r squared. There's no longer any dependence on the mass inside, no longer depends on the radius once you're outside the Earth. So that's kind of funny that inside the Earth, right, you get a force that's towards the center that is linear. Where have you met this before? Now again, it depends a little bit on what examples you spend time on in 161, but you might remember that a spring has a force to an equilibrium point that's equal to kx, some constant times displacement from the equilibrium point. If you're on the left, the spring pushes you right. If you're on the right, the spring pushes you left, with a force that increases linearly with the displacement. So we draw this, right? Some wall, here's some mass, here's some spring. If you squeeze the spring, it's pushing right. If you stretch the spring, it's pushing left. Right? So if this were here, it's squished here, forced to right. If it's over here, forced to left. Right? So in our case, x is the displacement from the center of the Earth, and the constant k is just this. So it's almost like if you did the following. If you have your Earth and you dig a giant tunnel to the center of the Earth. Yes, I know it's full of magma, it's not going to work, but let's pretend it works. And you drop something, or you jump, right? You're going to oscillate just like as if it were a spring. Now you're going to learn more about springs in Phys 163. It's kind of a shame we haven't done that already. But this falling back and forth through the Earth, you fall to the center, you get attracted here, but then you overshoot because of a lot of speed. You keep falling back and forth through the tunnel in what's called simple harmonic motion. Because there's the restoring force towards the center that's linear. Of course, the assumptions here being you're not going to get killed by magma. The density of the Earth is actually uniform, which it's not. So it's a lot, it's a very theoretical idea, but it's a cute little idea. Okay, so this is one example of Gauss's law of gravity. Now, you can think about the analogous example with a charged ball that has uniform charge per volume, and charges spread throughout the whole volume. But I'm going to give you a little challenge, and the challenge is this. The Flat Earth Society claims that the Earth is flat. And let's just suppose, I don't know what exactly they claim, but let's suppose it says the Earth is a flat, infinite sheet. Of some thickness. Right, some thickness, let's call it thickness h. And suppose it has a uniform mass density rho. So Greek letter rho looks a bit like a curly P. So what this is saying is that pick a chunk of, pick a cube of Earth here. What is the mass per volume? Like 1 cubic meter, how much kilogram of Earth is in that. That value, let's call it rho, is constant everywhere. It's an infinitely long sheet. Question. Challenge question. How thick is the sheet? In other words, we're going to find h. Such that we feel g equals 9.8 meters per second squared. For rho, what value might you pick there? And we could either pick the average mass density of the Earth. So you just take the total mass of the Earth divided by the total volume of the Earth. You can look those up or work those out. And use that value, this kind of average the whole mass of the Earth, or you can just, look up what's the value of, for like, say, a rock. The rock might be a couple of 1,000 kilograms per meter cubed. Doesn't matter, right? The or you just leave it as generally as rho. Doesn't matter, right? The method is what matters, the thinking about it. So this is the challenge problem. I'm not going to answer that, but my colleague Nick, Dr. Underwood, promised that he'd go through that on Monday, the 20th of April. Right, so next Monday, if you're watching this shortly after this video gets posted, in his live streamed lecture, he promised me he's gonna go through that problem. So you have a week to figure it out. If you figure it out, that fills me with confidence that you've understood Gauss's law, including how it is applied to gravity. Okay, that's enough examples. There are lots more we could do, but one thing I want to say is that we have covered all the possible symmetries you might encounter. Spherical, cylindrical, and the sort of infinite sheet symmetry. So if you can think about all of those and apply Gauss's law to each of them, then the rest is just details, right? Say in the cylindrical case, is it an infinite rod? Is it an infinite pipe? It's hollow on the inside. Is it a rod inside a pipe? Lots of examples. They all boil down to the same thing. So once you have a few examples under your belt, applying Gauss's law is going to be easy, and you'll never want to go back. Okay, that's enough from me about Gauss's law. Now get practicing.